Cool. Semester starting okay? All right, let's get started. I think we'll have plenty to cover today, so we can go ahead and run on into it. Just a few announcements. I'm going to put recordings on Kaltura, so you'll be able to watch them on Canvas. I forgot if I've actually pushed a button to release the recording from Tuesday. If I haven't, I'll do that today. In general, I'll keep posting there. In terms of where we are for our class, we're actually starting to get into the real content of the class today. So we are going to mostly talk about attention today. And that's an operation that's kind of the fundamental building block for pretty much all major large language models and most foundation models. So we'll talk about that. We'll talk about how you take attention and start building up these layers with it. Those layers are going to be very useful for us. And then on Tuesday, we'll return to this issue. We'll talk about how there are certain aspects of transformers that are pretty computationally painful and what we can do to get rid of those aspects. So we'll talk about these new subquadratic architectures. And then in a week and then following, we'll actually use all of these tools we've developed to build language models. And we'll also see kind of how we adapt them for building foundation models that are multimodal as well. And then finally, we'll get into how you actually use language models, stuff that you guys have seen before. Any questions about where we are? We might also release homework 1 next week, potentially. TBD. It's either going to be next week or the week after. All right, awesome. So let's get started. What we're going to start off with is this very basic operation. We'll try to build some intuition for what attention is. It's a little bit what the word sounds like, but we'll see that there's a more technical meaning for it. There's different ways of using attention. We'll talk about one where you're using it on itself. So this is called self-attention. And then we'll use kind of the intuition and the ideas we've built up to build a very simple layer. And then we're going to see exactly how this works. And once we've built up this layer, we'll add a few kind of more complications to it. We'll do something that's called multi-head attention that gives us more flexibility. And then finally, we'll use a trick to try to make sure that our models can figure out the fact that order of words matters in sentences. So we'll see what that means in a second, but that's going to be called positional encodings. And then once we have this basic building block down, we're going to go from there and build it into an architecture that's called a transformer. It's developed for translation. So it's called a transformer because it was meant to translate or transform one language to another language. We'll see that it works on language more generally. And we'll talk about the very basic setup. Later on, we'll use this to build language models, generative models, et cetera. Any questions so far? All right, let's go ahead and jump into the first part. So here's a very, very basic history of this attention operation and kind of where it came from. The motivation is very similar to what we talked about last time. We said that we have these recurrent neural networks. These are models that can apply to sequences, including sequences of words. All that language really is just those sequences of words. But we had one issue. In a recurrent neural network, we have this state, right? We have this vector that has all of the context that we have about the sequence up to this point. So we have to compress all the information that we've ever seen in the past into this fixed length vector. And that could be a problem because it might turn out we forget relevant things. Especially when you're thinking about words and sentences, they have all kinds of interactions and dependencies with each other. And those things might get lost when I'm compressing everything into this fixed length vector. So this is really the motivation for this attention idea. We have these very basic intuitions about language. Words depend and connect to each other, and they have some complex dependencies, and we want to make sure that we preserve that information in our models as much as we can. Okay, so here's a picture from one of the papers that initially defined attention. As I mentioned, this was something people were really thinking about for translation. So what you're seeing here basically is kind of the way words relate to each other across a pair of sentences, which are the same sentence, but they're versions of each other in different languages. So on kind of the y-axis here, you're seeing it in French. On the x-axis on top, you're seeing it in English. Okay, now one of the points of this plot is to basically tell you that when we do translation, you can't do it word for word, right? There isn't a one-to-one relationship between a sentence and the translated version. And you can kind of see that already, right? You can see that there is some dependence on the diagonal, which are the kind of words that directly match up on positions, but not always. You have some kind of actually almost opposite diagonals as well. But you also have, in addition to sort of the word that you're matching, some dependence on other words as well. So somehow we need to take care of this information, right? And as you can see, these dependencies can be as complex as you'd like, so we have to be careful not to forget any of them. Okay, so attention is going to be a mechanism to help us model this idea. And there's been lots and lots of different versions of it since back in the mid-2010s when people started introducing these things. And we're going to see one very simple version of it that's going to help us in general. It's going to be called self-attention. Okay, everybody okay with this very high-level intuition? Cool. Okay, so let's go ahead and try to come up with different ways of creating this attention operation. Let's do it from the bottom up. And what we'll do here basically is that we'll first build an operation. So this is going to be something very simple, right? It's not going to be a model in itself. It's literally going to be some function. And the function is going to have some inputs and some outputs. And that's going to be our self-attention function. So this will be at the lowest level. And then afterwards, we'll use this as a building block to build what ends up being a layer for a transformer or a transformer block. And then from there, we'll put a lot of those together to build up a language model, like a transformer. So that's the thing to keep in mind for today's lecture. We're going to have these kind of 3 layers of abstraction, a very low level where we're just defining this operation called attention, a higher level where we're building a whole block that includes attention but some other things, and a higher layer than that where we're building a model out of a bunch of blocks. So that's the thing you want to keep in mind as we go, but for now, we're going to start with something very, very simple. Okay, so here's our intuition. We have dependencies even when we're not translating. Let's say that we're just working with one sentence of words, and we like to do something with it. What that something is, we don't know yet. That's our general foundation model philosophy, right? Someone's going to come and give us some task later on. It's going to be built on top of our model. We just want to get some information, some content from our sentences. Now, one thing that we have to take care of is that we're going to have these dependencies between words in the same sentence, and we want to have some way of tracking that. So let me show you a simple example. This is also a very old figure. Here is a sentence. The FBI is chasing a criminal on the run. And what we're doing here is we're actually tracking words as we go through the sentence. So the red word is the one we're looking at currently. And intuitively, that makes sense, right? If we want to get information from a sentence, we'll have to look at every word. And that's what we're doing here. We're going through and we're tracking each word as we go from the first word to the last word. We're going to do that with punctuation signs and things like that as well. But the other thing to look at is, look, the current word is not independent of all the other words in the sentence, right? It has some relationship to some words in the sentence, but not all of them. And that's the thing that you're seeing in blue. Right? So for example, the second word that we're looking at in red is FBI over there on the second version of the sentence. The refers to FBI, right? So this is the idea for what we want to do here. We want some way to figure out which of these dependencies there are. And each time that we're getting information about a word, we want to let all of these other related words actually have some contribution to that information, because they contain some important information as well. All right, everybody agree with this intuition? Now notice I'm talking about it at a very high level. It's very vague. Our job is going to be to translate this vague intuition into an actual mathematical operation that we can carry out on these sentences. All right, similar picture over here, for example, right? So we're scanning through words, and there's various dependencies, and there's various strengths for these dependencies as well. So we're going to see how we're actually going to go build this up. OK, so we're going to have basically two real goals when we're doing this kind of information processing. Don't take these too seriously. It's just two criteria that are worth kind of thinking about. The first criteria is we are processing words in some sense. And what that means is we're going to convert them to vectors. And as we go through our layers, we're going to transform them in various ways. We're going to extract what's meaningful in these words. Now, the way to think about this is thinking back to our example with convolutional neural networks. We had one input, which is an image. It was some raw pixels. And we took that, we made it a vector. Then we passed that vector through some layers. And each time we created another vector at the output of a layer. And this new vector had some more abstract stuff in it. It had stuff that's more useful for whatever we wanted to do downstream with it. So same story here. We're going to do this with the words themselves. But we need something extra because these words aren't independent of each other. When we worked with convolutional neural networks, we could pass in an image, and that had no relationship whatsoever to other images. We could just run these transformations separately. Now we have the sequence of things that are tied together, so we can't just process each word independently. We're going to have to trace out some relationships between them. And that's going to be our second principle that we're going to use here. Let's enable some kind of interactions between words, because we know they have these dependencies with each other. All right, who has questions so far? Go for it.
Why can't you simply apply CNN over a matrix for like every embedding vector for every word we have? We make a matrix of 10 words and apply one kernel over it.
Ironically, we will be able to do that. But here's one reason why it's not so simple. Let's suppose we're doing that. What size filter would you use?
We should try with multiple filters because we don't know which word will be connected.
Sure. So let's say we have a sequence of length n, and we're going to run a k by k filter, right? Just as we would with a convolutional neural network. Well, what's the problem? If k is anything lower than n, there's going to be interactions that we miss, right? The meaning of the sentence might have a lot to do with the third word combined with the 400th word, right? Those kind of long-range interactions have to be accounted for. But that also means your filter has to be huge, right? Because it has to capture the whole sentence. So here you're describing a filter which is literally the sequence length itself. And that's a very inefficient model, right? But we'll see that there's ways to make it more efficient. And next lecture, we'll talk about something along those lines. So you're kind of getting in advance of what we're going to do here. Cool, great question. Other questions? Yeah?
Are the word vectors we're using in this case going to be the vectors of the individual words themselves, or are they going to be context-aware word vectors?
That's a great question. They're actually going to be fixed. They're going to come from a lookup table. However, we are going to train them end-to-end with our model. So rather than saying I train them separately, as in the classical word-to-vec sense, and bring them in, I'm just going to create empty vectors, initialize them, and train them with my whole model. So they are going to contain relevant information. But the contextual part will go upstream of these word vectors. We'll see that in a second. Cool, awesome questions. Other questions about high-level story so far? All right, let's start building in that case. OK, so the input is going to be just what we talked about here. These are going to be vectors for words. That's what we mean by embeddings. Now, I'm being a little bit loose here. I'm going to talk about words just for intuition. In practice, we don't really work with words. We take our raw sentences, which are just plain text, and we're going to run a function called a tokenizer over them. So the tokenizer is going to take your raw text input and output a sequence of tokens. Now, there's different tokenizers that you could potentially use. There's some very popular ones. If you have an NLP background, you've played around with these a lot. But really, what we have are these tokens. And for each token in our vocabulary, which is going to describe all the possible tokens we can use, we're going to assign it a vector. And this vector is going to have some dimensionality. Depends on the model that we pick. But we're going to have one of these vectors for a token, or in our informal sense, a word. OK, everybody OK with this? Great, so let's take an example. And I will admit that I stole these pictures from an online resource, which is quite nice. I advise everybody to go read this thing. It's called the Illustrated Transformer. It's a really nice breakdown of a basic transformer. And it has really nice figures that I've used repeatedly in these slides. Cool, so here's the story so far. We have a sentence with 2 words. The 2 words are thinking machines, like the company. And what we're going to do is, of course, tokenize them. But really, we're not showing that. And then we're going to assign 2 vectors to these. And these vectors are going to be called x. x1 is the vector for the first word. x2 is the vector for the second word. Where do these vectors come from? A table, basically. So in my table, I have my vocabulary. It contains all the words in my language. Thinking and machines are 2 of those words. And then I'll look them up in that table and get the corresponding vectors. All right, everybody OK so far? Let's start this idea of taking our 2 criteria and instantiating them. So let's go ahead and build up some intuition for how we could capture these interactions that we're talking about. Right? So right now, there should be some interaction between thinking and machines, because the word thinking pertains to machines. Machines is the subject in this case. So this is a very language kind of idea. Let's translate it to math. OK, and for this, we're going to have some very simple intuition that you want to recall. It's based on the notion of retrieval, which is used all the time in all kinds of systems, including search. Right? We're going to design interactions based on a very simple retrieval idea. Here is one example of a question that we'll try to answer. Which restaurants near me are open at 9 p.m.? OK, now if you actually type this in Google, it'll give you a response. And people have built systems that can answer questions like these for 30 or 40 years. But the very basic idea for how it works is you have a query, and you match it up with a key. So the query is which restaurants, and then I have a key. I want them to be open at 9. And depending on the query and key interaction, I'll get some values. And of course, this is something you've seen and you're comfortable with. This is going to be our high-level analogy. We're going to say, OK, well, for this particular restaurant, the query and key have some score. This is how much they match up. It's 0.3. In a different case, they have some other score. It's 0.7. And when I go report back to the user what I found, I'm going to show them some combination of these things based on what scores I get. OK, don't take this too seriously. This is not a real retrieval system. This is just an analogy. But we're going to use the same basic idea for processing these interactions in words. And again, notice that there's 3 things here. We're going to have a query. We're going to have a key. The query and key will be compared in some way. That will produce a score. And then we'll output values based on these scores. That's the basic operation that we want to translate to words and word vectors. All right, I saw a question.
What's the difference between the query and a key, like,
For us, it's not going to matter.
It's not going to matter.
It's going to be, we're not going to really create any formal characterization of that difference. We're just going to permit words to act as both queries and keys.
So any word can be a query or a key to any other.
Yep,
Well,
exactly.
there.
Exactly. And we'll see that in the next slide. Cool. Other questions about this? OK, so one more time, we have this analogy of retrieval. For retrieval, we want to answer some query. We do that by comparing the query of a key. Depending on the scores we get from that comparison, we output certain values. Now, our job is going to be, let's do this exact same thing, but we're going to now do it for those word vectors that we talked about. OK, so let's see how we're going to go do that. We said that we're going to want these 2 operations. We're still working on the second one, which is enabling the interactions between the words. OK, so the very first thing we'll need to do, since we're going to compare queries and keys, is to figure out basically where we get the actual queries and keys, given that we currently just have our word vectors. We have those x's. All right, what's the simplest type of transformation we could apply to a vector to get some new vector? OK, maybe not quite as simple. Sure, OK, the identity transformation may be the simplest. What is a simple one in general?
Just multiply with a matrix or add values.
Yes, and what is that called? Sure, we're just going to call them linear, because for some reason machine learning people don't know the difference between linear and affine. So let's call all these things linear. Okay, so basically in ML in general, the simplest kind of transformation we deal with is a linear transformation. And we said we need queries and keys and values. All that we currently have is our word vectors, so let's go ahead and transform them. And this transformation will be a linear transformation. Once you fix a basis, any linear transformation is just a matrix vector multiply. And that's what we're showing here. We started with the two things on top over there, thinking and machines. We have their word embeddings. Those are vectors, x1 and x2. Well, now we're going to have 3 linear transformations, one for the query, one for the key, one for the value. A linear transformation is just going to be a matrix. And we're going to go ahead and matrix multiply WQ over there with x1. And we're going to get Q1. We're going to do WQ multiplied with x2, get Q2. Everybody okay with that? So we do this for the queries. We're going to do this for the keys. We're going to do this for the values. I'm going to have 3 different linear transformations. All of them are represented by a matrix. All these matrices have to be compatible with the dimension I have for my embeddings. I'll perform these multiplications, and I'll get a query vector, a key vector, and a value vector for all of the elements in my sequence, for all of the words. So if I have a sequence of length n, after I do this operation, I'll have 3 times n vectors. That sound okay? Cool. Now notice that these 3 different weight matrices over here, they don't have to be the same. They can be different. And the other thing that you want to think about is, I'm showing you this model as if it's already trained, and you're running it. But of course, it's good to keep in mind that this is a model. It has weights or parameters. We are going to train them. Well, these are precisely the actual parameters that we're going to train, these matrices. All right, everybody comfortable with this at this point? Go for it.
Why only these 3? Why we had 4 weights or 5 weights? The intuition is okay, but let's say we are taking 3 weight matrices. We can take 4 also. We can take 5 also.
What would the 4 or 5 refer to?
Maybe context or condition something.
I think you could probably design a more complex model that would have extra things. But these 3 things are actually pretty fundamental. You could actually compress them into one thing if you tried. We'll see that in a second. But basically, you want something that allows a comparison. That comparison needs 2 things. One thing is when you're the word being focused on. One is when you're one of the other words that are interacting. So you need those 2 things. And you want those comparisons to produce some value. So you need a third thing. So this is probably like the simplest thing you can do. Anything else, yeah, you could design a more complex model, but it might not help you. Cool, so we have now our initial word vectors or embeddings, and now we took these weight matrices, 3 of them, query, key, and value matrices. We performed this linear transformation, and now for every word in our sentence, or more broadly, for every element in our sequence, we have these 3 vectors. Now let's go ahead and continue building up that analogy to retrieval. We said that we want to compare the key and the value, the key and the query. And based on that, we're going to do something with the values. So let's go ahead and actually create that exact comparison. We're going to call this the score function. Again, we have our color-coded 3 vectors over here. We said that this is the operation that we want to do. Compare the query and the key and get a score. OK, what kind of operations can you apply to 2 of these vectors that perform a comparison and output a score? Yeah, dot product is a good choice. Of course, it's not the only choice, right? You could do lots of different things. You could even learn a good operation here. And in fact, initially, people had all kinds of pretty sophisticated operations. It turns out that, as is often the case, simpler is better. We're going to run dot product attention, but it's not the only kind of attention. It could be other things as well. But OK, let's say I take my query and key vectors. I do my dot product. I get some value. Maybe it's a low value if they're not very aligned. Maybe it's a negative value. Maybe it's a high value. I get something. And then I'm going to do this operation on all of the different keys that I have. So I'm looking at a word. I have its query. I'm trying to figure out the interactions with all of the other keys. I go ahead and compute this dot product for all of these. There's n such dot products, where n is the length of our sequence. And then we'll run softmax. And that's going to normalize all these things. It's going to give me something that looks like probabilities. Everybody okay with this so far? Okay, we'll see it in a second in more detail. Now, just to make things slightly more fun, I'm going to do a little bit of scaling, and we'll see this in just a second. Here's where we are so far. We have our embeddings. We transform them with our query, key, and value weight matrices into these three vectors. And now I go ahead. I'm looking at the first word. I'm processing this one. That is thinking. And what I'll do is go ahead and compute scores. I do it for the word thinking and its query with every key in my sequence. So that's what's happening at this operation here where you see the score. I'm doing Q1 dot product K1, Q1 dot product K2. If our sequence was longer, I would be doing all the other elements as well. It would be Q1 dot product all the way up to N. Everybody okay with that? So what am I really doing here? I'm saying, oh, I'm looking at the first word in my sentence. What other words in my sentence have some interaction with this word? I'm trying to figure that out. And based on this, I'm trying to say, hey, how much should I care about all the other words in my sentence? How much should they influence what I'm doing as I'm sending this word through a layer? Okay, so once we have these dot product scores, we're going to do a little bit of scaling. So we're going to divide by something. You can safely ignore this for now. This is a normalization trick, but it's not super important. And once I have these values, which here are 14 and 12, but again, you would have a whole sequence of them for a longer sentence, I'm going to go ahead and run all these guys through softmax, and I'll have these values. They will be between 0 and 1. Typically, there'll be larger ones for more influential words. So over here, I got 0.88 for the word itself, which kind of makes sense. Usually, you're pretty dependent on yourself. And then 0.12 for this next word. And of course, if perhaps there were some third word over here, and this dot product comparison was very small, I might get something close to 0. Might not be very influential. All right. Any questions so far? Yeah.
What are the dimensions of weight matrices?
Up to us. They have to be compatible with the word embeddings because we're going to do that linear transformation. But afterwards, we get to set that dimension. It's called dk over here, but that's up to us. We can make them larger or smaller depending on how large we want our model to be. There are some efficiency issues, though, if we make them too big. Yeah?
Can I ask why the normalization is square root of dk instead of just like the normal like a percent similarity where they just divided by the product of the norms of the two vectors being inputted?
Yeah, I mean, this is just a practical trick. This keeps the expected norms of these vectors to a certain range. That's why it's designed to be that way. You can actually trace out the math. It's not super hard. But it's not like critical that it be exactly that. You could do it differently as well. All right, so the story so far is that we are working through a sentence. We are looking at each word. We are trying to process the representations, the vectors for those words. But we're also trying to permit some interactions with other words. The way we kind of mathematically formalize those interactions is through these queries and keys. The query and key dot product comparison produced a score. These scores end up getting softmaxed. And this gives you some value that says how much I should influence other words. So I'm looking at the first word, and it itself has some influence, and some other words have some influence too. All right, now we haven't done anything yet with the value vectors. Let's go ahead and do that. So still exactly the same picture for what we've done so far. Okay, now we're going to go ahead, take our softmax values. We're going to take all of the value vectors and multiply them by their corresponding softmax value. So I have 0.88 and 0.12. I already had all my value vectors over here. Take each one, multiply it by this softmax value that I have, and then just add those things up. So I have this linear combination of the value vectors, but the weights on it are coming from these softmax values. And I just go ahead and use that as my output for this particular word in my initial self-attention layer. That sound good? So what's really going on here? Well, basically what I'm saying is I'm going to start with a word as shown in X1 over there. I'm going to run it through a layer. This layer is doing some processing for it. And this processing is saying, hey, I want some contribution from myself, but also from all other related words as well. How much should that contribution be Well, it's determined by the scores that are coming from the dot product in the operation. Sound good? Now, can we easily understand exactly what's happening here? Not really, right? This is just a mathematical operation that we've created. The only thing that matters is that it kind of captures the intuition for what we set out to do. We said, hey, we're doing processing of words, and we want to permit interactions between multiple words in a sentence. That's exactly what this is doing. Now, notice what would happen if these words were totally independent of each other, had no relationship at all to any of the other ones. Then what you'd get here in the softmax is a 1 on the word itself, 0 everywhere else. The value vector would only come from the word itself and not any of the other ones. So if you really had a situation where all the words were totally unrelated to each other, this thing would collapse, basically. I wouldn't need to do anything else. Questions? Anybody confused? OK, sounds good. Let's go ahead and find a cleaner way of writing these guys. Right now, everything is written with this kind of ugly form, where I go ahead and I kind of write a bunch of dot products. How many total dot products are we doing, by the way, as we scan through a sentence? Yeah, n squared, right? Because for each word that I'm looking at, I'm going to take its query and multiply it by the key for every other word and itself. So that's n total operations for a sequence. And then I move to the second word, the third word, and so forth. I'm doing it each time. I get n by n, so n squared such operations. This is the reason why in the next lecture, we're going to try to find ways to make it more efficient than this. If my sequence length is very long, this already is a very expensive operation. All right, so let's go ahead and write this in the compact way that I promised. It's going to look extremely simple, right? So all I really need to do is take a matrix that contains all of these word embeddings, one vector for each word in a sentence. That's this capital X over here. To get my query vectors, I do the linear transformation. That's x times WQ. So rather than saying it's a matrix vector multiply that I apply to each word vector, I have a matrix multiply. And now it contains all of my query vectors. Same exact idea with my key vectors. Same idea with my value vectors. So I transform all of them into matrices. This is just for notation. It makes things nicer to write down. Then my attention operation is actually something very, very simple. I can write it in the most compact form like this. It has 3 inputs: the query, the key, and the value matrices that we just wrote down. And all it does is run softmax on the query times key matrix multiply, do that little normalization that we talked about, and then take those softmax scores and multiply them by the value matrix. And to write it kind of in a full way, this is exactly what we talked about. We take x times WQ. That's all of our query vectors. We multiply them by x times WK. That's our key vectors. Normalization, softmax, multiplied by the value matrix. So this complicated looking thing that we did, it has an extremely simple and clean equation. And this is just one basic operation. This is the self-attention operation. OK, everybody OK with this? Yeah?
I'm a little confused by how the value matrix being multiplied into this corroborates with the original definition of value that we used earlier, where we assign value based on our perceived relationship between the query and the key.
So we should think of it slightly differently. There's value and output. So the output depends on the values and that perceived relationship. The values are fixed in advance. And then I say, I'm going to give you a combination of those values. And that combination is what depends on that comparison.
Gotcha.
Does that make sense?
Yep.
Cool. So we designed an operation. And the cool thing about this is not some complicated operation that you could never think about implementing, right? The basic pieces here are exactly what you know how to implement in any ML model, right? We're talking about linear transformations, matrix multiplies, softmax. That's kind of it, right? So this is something you could write in PyTorch in like 2 minutes. And that's also one of the reasons for why transformers are so popular. We are not doing something radically new and different. We're just repurposing a bunch of operations that we feel very comfortable with already. Cool. All right, let's take our first break there. I can answer more questions about this if anybody has questions. If not, feel free to hang out for a few minutes.
So the matrix X, each row corresponds to vectors.
Yes. Yep. Yeah, so X over there is going to be, you take your input sentence, you get the vectors for each of the elements in the sentence. Correct, correct, yeah. Yeah, here we're showing this as if we've already trained the model, and you have those weights already, yeah. Yep. Correct, yeah.
What's like multiply this times v is actually how this works like the whole thing.
That's right, yeah. So that softmax thing is itself a big matrix, right? And what it has is, for each word I'm looking at currently, how much softmax score I'm applying to each of the values that get multiplied together into the output. And that whole expression is actually giving you the output vectors for every element in the sequence.
When we talk about embedding, I'm just looking at, like, for example, I have the sentence thinking machine, right? Do I have just embedding thinking and machine? Also thinking machine and
No, just each element of the sequence. I have two elements.
I'm in bad.
Oh, no, no, no. There's no connection to that here at all. We're going to completely ignore older language models. So this is going to be something that doesn't use any of that. That would complicate things quite a lot, and it would add more complexity, so we won't bother with it.
He's actually in my mentoring committee.
Yeah. Second?
What is DK?
Dimensionality of the key vector. So this is another dimensionality that we have to fix. The dimensionalities are going to be basically first the embedding itself. Then after that, I have to have query, key, and value dimensionality. The query and the key have to match up because I'm doing dot product, so those have to be the same thing. Then the value vector, it'll turn out there's a certain way to set it. It's also not completely free. But if I choose these values, then I've kind of designed my model, so to speak, right?
why is this the square root of dk instead of dk? Why is it the square root of dk instead of dk?
Oh, so if you set it to be dk, you're actually flattening things out by a lot. So that division basically is saying something like this, right? If you don't divide at all, the values are typically so big that one thing will get everything. It'll be the probability 1, everything else will be 0. And if you divide by a lot, you'll kind of flatten, make everything the same probability. There's sort of a correct normalization that on average, right, so like statistically on average, it gives you something where you're not doing either of these extremes. Not one big probability, and not one exactly uniform probability. That's why you're setting it to be square root. Yeah.
Is it necessary to have them square match?
For the weight matrices, no. In fact, typically they're not, yeah.
And second, every like word it has really good things. So if we are taking eventually softmax, how does it matter we need to divide?
Say that one more time. I misunderstood your question.
So DK would be constant, right?
Oh, yeah, yeah, correct.
It's across the
Yeah.
whole model.
Yes.
DK is one only. So if we're dividing it, how is it matter?
Oh, it does.
We are applying softmax.
It controls the sharpness of softmax, right? So basically the issue over here of softmax is, depending on how big those two vectors being compared are, those will produce a certain magnitude, right? It could be pretty big, potentially, or it could be pretty small. If those are all pretty big, then what happens in the softmax is the dominant one will get probability 1, everything else gets flattened. If they're all pretty small, you end up getting very uniform probabilities. What you want is to be somewhere in between. So you need some normalization for that. But that normalization can't be constant because you don't know a priori how big these guys will be. They kind of depend on how long these vectors are. And it turns out this square root of dk is the thing that on average normalizes things. This is coming up a lot, so maybe I'll draw the calculation for you guys. It's not super challenging.
And also like in the
Yeah. Oh, do you mean like the 8? No, that's just experimentally set. It could be other things. In fact, I don't think it's 8 for all models that people build. But yeah, there'll be a few magic numbers. This is like the original Transformers model. It's not all like inherently right or anything like that, but yeah. But the decay does matter, that you actually need.
I had a same question like why are we dividing here? So in order to bring something in like
Exactly, yeah. Yeah, and again, the intuition you want to think about basically is like, depending on how these actual values look like, either you always get all the attention on the word itself, which is useless. That's like, again, the independent case. Or if they're too small in magnitude, you end up getting very flat, uniform probabilities. That's also useless, right? That doesn't, determine anything between the difference of like relevant and not relevant words. You want something in between, and this is the thing that on average gives you that intermediate behavior.
Oh, I see. It's just
Yeah.
a
Yeah, so the only thing I ever really do here when I talk about interactions between words is I want whatever processing is happening for my word to get impacted by other words. And by adding a little bit of their value vectors, if they make a difference, that's what I'm allowing us to do. So this is literally all that our interactions means here. It means adding a little bit of the value vectors from other relevant words. That kind of makes sense? Now, I mean, these answers are not always satisfying, but the way you should think about this is, we'll let the model figure out the details. We just want to permit it to do some abstract operation like this interaction. Yes?
A quick question. So I'm not sure why we don't sum for the attention definition. Because there's a sum.
We are summing. That is this last matrix multiply. It is summing up.
Oh, you're
Yeah,
right. Okay.
trace it out. I mean,
Yeah.
I know it's very annoying to see it in this matrix form, but if you look at it, there will be a sum.
Okay. And the values are associated with the keys. Is that correct?
No, the values are something else. They're independent. We're going to
Okay.
compare the queries and keys. That comparison will go into the softmax. This will produce for us some weights, and then we're going to multiply the value vectors by the weights and add them together. But we're not going to have any other more direct relationship between the values and the keys.
So value exists for every query key combination?
Yes, so every word will get three things, query, key, and value. It's just that the query and key get compared directly in the dot product, but indirectly, we're going to take that output and do something with the values.
Okay, but when a query and key match, both of those words would have a value attached associated to it.
Every word has a value attached to it, yes.
And which value?
Every word just has one value vector. It is the only one that you have.
I understand that, but if you have a query and a key and they match up,
Yep.
they both have values, right? But you only choose one of the values.
Oh, sorry. The queries and keys don't have a value. A word has separately a query, key, and value vector.
Okay, sure.
So it's not like a value per combination of query and key. It's a value per word.
Okay. I'm not sure I follow 100%.
Let's go for it. No worries.
Yeah.
I think the way you're thinking of it is you're saying, okay, well, for a query and key, right, if they match, then for that combination, in some sense, there's a value
That's
vector.
exactly, yeah.
Right, but that's not the case. There's always a value vector for every single word.
Okay.
How influential that value vector will be is a function of how big this, query key alignment is. But it's always there, right? And you're always adding it in. It's just that it might not have a big contribution if that query and key don't match up, or it might have a very big contribution if they do match up. But it's still always there, and there's always one of them. It's not one per pair, it's one for the word you're looking at.
Yes, but there's two words, right? There's the query word and the key words.
Yep.
Which value do I use?
So what I'm going to do, let me actually go back. We're almost there, so we are 99% on the same page. All right, so this is where your question is. What I'm doing right now is I'm trying to get an output for the first word, and that output will be a linear combination of all of the value vectors. Now the question is, the weights of that linear combination, what should they be, right?
Yeah, okay, yeah, I missed that. Okay, yeah, thanks so much.
Yeah, absolutely. All right, everyone asked great questions. Please interrupt me and ask more questions if you're confused. Today is the day to get all of these basics down. So please stop me some more. We'll talk through all of these. Let's keep going with a couple of more extra bonuses, and I'll keep it short. Now we need to think about taking the basic operation and using it to actually build a layer. And to do that, we're going to have to do a few more things that we've ignored so far. OK, so let's take a look at the very first thing. We're going to talk about something called multi-head attention. So far, we defined a single attention operation. And we might say, hey, running a single attention operation per layer, maybe that's sufficient. Unfortunately, one attention operation may be capturing one kind of behavior, one kind of interaction. And maybe ultimately that's not enough. And you kind of have an idea of this already, right? When you think back to convolutional neural networks, again, that's our analogy. We didn't say, hey, there's only one single filter for a layer, right? After all, one filter could capture one pattern that we care about, but maybe what we really need is 50 patterns or 400 patterns. So what we did there is we said, OK, there's going to be multiple filters. Everybody remember that from previous classes? Right, so we're going to do the same exact trick here. The equivalent of multiple filters, we're going to call it multiple heads in attention. And it's going to operate more or less exactly the way you would think. We're going to run in parallel multiple attention operations. All of them will still produce an output. The output, again, is that weighted linear combination that we had. We're just going to do this multiple times. And why do we care about doing this? Well, we're letting our model figure out what behaviors should be captured in all of these different attention operations. So we're going to draw the picture from before, but we're going to do it multiple times. So notice I still have all of my word embeddings. They are what they are over there. That doesn't change. We're not doing that multiple times. We're now going to have a ton of these different query key and value vectors and matrices. Here, how many different heads do I have, just from glancing at this picture? 8, right? I have 0 through 7. Okay, so now, when I have these different weight matrices, I multiply them by x. I go ahead and get these query key and value vectors, one for each head, so now I have multiple of these guys as well. I still form the outputs. That's these z's over here. These outputs are still linear combinations of the value vectors. But again, there's one of these for each head now. So I take these guys, and I stack them together over here into my output. And then I can run another linear transformation and get this very final output here, z. Everybody OK with this? I haven't really done anything. I'm just saying we're repeating the operation that we talked about multiple times. And we're going to finally compress it into one overall output that I'm going to have. So this is something that we'll do. Again, nothing special. We're just saying, hey, there's different behaviors here that we want to capture. So let's give ourselves more flexibility. Now, this more flexibility comes at the cost of multiple copies of weight matrices. But that's OK. And in general, we're going to ignore the fact that we're going to have tons of these different weight matrices. This is the reason why our models are going to be huge. Later on in the homework, we'll tell you guys how to compute the number of parameters that you get as a result of all these things.
So, if we are initializing every weight differently for every head,
Yep.
why they aren't coming to one minima point only? Like eventually, all the training data is same for every head.
It shouldn't be, right? These initializations are different. They're not identically. So in general, as soon as you do even one single SGD operation, these are going to be all different. Unless you have unbelievably bad luck, and they're all initialized identically, just randomly.
But they would be initialized differently, but eventually, like W0 shouldn't be approaching towards W1 and all.
Why?
Because we aren't changing anything else, right? We have the same data, we have the same training process for every head.
Correct. Yes.
So,
But the model is going to look for ways to become good at making predictions when we go train, right? That's just the basic intuition of training. And when that happens, it's going to need more flexibility inside these different matrices. It's going to need to capture different behaviors in the different heads. If it tries to do exactly the same behavior in each head, it's going to be very limited in what it can predict. In fact, it'll get stuck at something very, very low performance. Do you see what I mean? All right, let's talk about one more thing, which is going to be the most slightly annoying thing that we talk about today. So far, everything we've said has basically completely ignored the fact that there is some meaning to the words in our sequence. Right? So whenever we do these operations, we said, OK, we're going to do it for element 1, element 2, element 3, and so forth. And each time we compared element 3 with all the other elements in the sequence, that was our basic dot product attention. Everybody agree that's what we did? OK, now so far, if I randomly permute the elements of my sequence, what changes? Everybody see what I mean? Let's say I swap word I with word J. Does anything change in all the things I've done so far? Not really, right? I mean, I'm still going to compare with all the other words. Nothing special is happening. So in other words, so far, what we've done is basically ignoring order. It's ignoring position. And that might be fine for some forms of data. But in language, of course, we actually do care about positions, right? There's some information carried in the fact that I have the words in a particular order. If I randomly permute them and change those orders, you get a different sentence or you get nonsense. So somehow we have to inject position information into our layers And we have not done that so far with our basic attention operation or with multi-head attention. Intuitively, does that make sense for everybody? OK, so let's figure out how to do that. OK, we're going to try to create some information about position. And one simple thing to do is maybe I could just go ahead and add it into my word embeddings. Now, the simplest thing you could think of probably is to say, hey, let's concatenate position information with our word embeddings. Everybody agree? So what does that mean? I could say something like, hey, take my word embedding for word 1 in my sequence and attach the value 1 to it, right? And then take my second word, attach the value 2 to it, and so forth. OK, so that's kind of the simplest way that I could insert position information into my sequence. And then because those are my new word embeddings, that would sort of go through into the attention layer. That's actually the intuition we're going to use, but it's going to turn out that attaching integer values directly is not super great for model performance for a bunch of reasons. So the first thing that we're going to do is not even attach or concatenate this information. We'll just directly add it into the word vector for every word. Now you might say, OK, well, I can add 1 to all the positions in the first word, right? And I can add 2 to all the positions in the second word's embedding, and so forth. Well, this also doesn't work great. And you can kind of guess why. One reason why we don't want to really do that is, of course, might turn out the values in those vectors are pretty small compared to adding in these integer values, like 300 or something. Everybody see what I mean? There's some values inside our word vectors. If I just add arbitrarily large integers into it, I might drown out that signal. So we're going to have to find some other things, ultimately, to add in that carry position information but don't mess up our vectors too much and don't mess up training too much. All right, so let's see one typical example. It's unfortunately extremely mysterious, but we'll talk through why it is what it is. Here are the things that we're going to add into our word embeddings, at least in the original transformer model. They're called positional embeddings or encodings. And here's kind of how they work. I am going to say that for the if word, which is the if element of my sequence, I'm going to go ahead and compute this guy. OK, I actually always confuse two things. What index is position and one index is I. And I get this wrong every time. So please check up on me to make sure that you don't get it switched, although it's not super important. So what we're seeing here basically is two things. One is like the position I'm at, which is the index that I am at in the sequence. And the other thing is the actual entry into the embedding vector itself. So position is the first one, the I is the index. And I was about to say it wrong, so make sure you pay attention to which way is the correct way. All right, everybody OK with this formula? All I'm saying basically is the following. I'm saying, hey, if my word is in the 13th position, I'm going to take my word embedding for that word, and I'm going to add something to that vector that indicates that it's in the 13th position. And there's going to be a formula for this indication. And this formula is given by this guy over here. It's a bunch of sines and cosines. Sine if you're at one index, cosine if you're at a different index. Everybody OK with this? I'll explain why it is like this in a second. But does the intuition at least make sense before we talk about anything else? Yeah?
So this sort of imposes a rotational effect almost.
Yes, we'll get there in a second. That is the reason for why it's like this.
OK.
The reason why I care about these rotations is I want to have some kind of predictability. I want to be able to say that the gap between the 0th and 15th word is the same as the one between the 15th and 30th. And that rotation matrix gives me that.
Yeah, I guess my question is what happens if we go all the way around the rotation, or is that just physically impossible? Given the
No, we'll keep going past, right? These things are periodic functions, so nothing bad can happen.
What does I do?
So there's two things going on. Position is where I'm at in my sentence. I is the location in my vector, right? So I have words. They're at different positions. For each word, there's a vector with some number of components as dimensionality. I indexes into that. Cool. So here's kind of the picture that we're going to show. Very similar to before. I have my sentence. I have my embeddings for this sentence. Here, there's 3 words in the sentence. So my embeddings are x1, x2, x3. I'm going to go ahead and add in some vectors. These vectors contain this positional information that I'm talking about. And I need some way of computing what that positional information is. It needs to have some properties, which is why it has this mysterious behavior. And those properties are going to be explained in 1 second, but this formula tells you how to get those values that you're seeing over there. Everybody okay so far? Yeah.
Can I ask why we decided to just do it in pairs? Like the first two are sine and the next two are just like cosine, and we'll just keep repeating what? Like
It's actually alternating. It's sine, cosine, sine, cosine, yeah.
What I'm saying is just like why is it grouping it by numbers of 2 instead of anything else?
Yes, because this is the simplest 2x2 rotation matrix that I can do. I'll show you in a second, but this is not the only way we could do it. We could actually group them by more. And in fact, that's a more common thing to do currently. All right, so before we get into the details of why the formula looks like that, let's make sure we're all on the same page about the intuition. Again, I have my standard word embeddings. So far we've said, hey, plug them into my self-attention layer. But then we said, OK, that's not a good idea because we lose all information about where we are in the sequence. In other words, we become invariant to permutations, which is not good for language. So we said, OK, let's do this extra step. This extra step adds positional information into the embeddings before we go ahead and go into self-attention. And then we had some basic ideas. We said, hey, well, one way we could add positional information is for this first vector, we could add all zeros. And for this second vector, we could add all ones, because it's the next one. And this one could be all twos or things like that. That would be a very easy way to add encoding, or to do an encoding of position information. But we also said that's not actually very good for a bunch of reasons. First, those values could get pretty big, right? If I'm at the 800th word, then that would be a very large value. That could drown out the signal in these embedding vectors. There's actually a bunch of other properties that I really want to preserve. So we come up with designing this slightly fancy-looking scheme for how to take that position information. OK, so let's talk very briefly why it's these sines and cosines and so forth. OK, so here's sort of the intuition for it. We really want a bunch of things. We want consistent encoding. We always want to have exactly the same thing that we add to our embedding vectors, no matter what those vectors actually are. We want things that are smooth. It's not good if I add spikes to my model, because those are more difficult to actually optimize over. And then finally, we want something else called kind of linearity across positions. In other words, the jump from 1 to 50 should be the same as 50 to 100. And that's really what we're doing with these formulas over there. Right? One really, really simple way that you could encode location information is to get something like that binary encoding over there. Right? So that thing is showing you on the x-axis the binary for values that are in your sequence, 0, 1, 2, 3, blah, blah, blah. You're seeing that red dot on 37. Right? You alternate ones for the least significant bit. You alternate every few for the next one, and so forth. It's literally a binary encoding. All we're really doing is making that binary encoding a smooth one instead. So we're replacing that binary encoding, which is a bunch of ramps, with just a few sinusoid functions instead. Everybody OK with that? I'm still being very vague here. We could formally derive it. You can write these things as axioms and show that this is a solution to those axioms. But at least at an intuitive level, this is what's going on. Yeah? Oh, so that's the dimensionality of the model itself, right? Because we're only going to go up to however many elements are in my embedding vector. So for example, if my embedding vectors have 768 elements, which is common for these older models, then I need to add in these positional encodings that have length 768. So that I over there is going through from 0 to that number. And therefore, I'm going to have this periodic behavior where I divide by d model. This is just kind of sampling from a sinusoid. Yeah. Yeah.
What is good about the smooth?
Helps our model optimize. If you add a bunch of jagged things into your model at different places, then think of those gradients when I do backprop, right? They're going to be extremely sensitive. So I really always want to add smooth functions if I'm going to add something in, rather than the up and down kind of thing. All right, so this blog, by the way, is actually a pretty good explanation of how you derive these formulas. They're also in the original transformer paper, but they are slightly annoying to pull out. And I'll warn you about one thing. We don't really use these kind of classical positional embeddings anymore. There's a bunch of modern versions of these. Yeah?
Is it a trainable layer? Is it a trainable layer?
Not right here, right? Those are the formulas that are literally what we have. You just index entities based on the position of your word in the sentence and the index in the vector. So there's no training involved here.
We are not concerned about the derivative.
We're going to go ahead and backprop through it, right? So we're adding this guy to the embeddings. The embeddings are trained, so we do have to backprop through it. Cool, great questions. Let's take a look at kind of the very last element here. So what is the reason for using these sines and cosines? Well, the basic reason actually is that when you think of the formula for something like sine x plus some shift, right? That's this sine addition formula. If you think back to 7th grade when you took trig class, you had all these identities, right? Like sine of a plus b is equal to some stuff, right? And that was related to rotation matrices. That's exactly what we're doing here as well. What we're really saying is there's a certain amount of rotation you should do when you cross a certain number of positions. And if you want this to be consistent across a sequence, then you'll need to have this kind of encoding. Doesn't matter, it's just a detail, but there is an actual reason for these alternating sines and cosines. All right, so let's very briefly talk about what we do with positional embeddings in general these days. So these are, again, sinusoidal embeddings that were defined in the original Transformers paper. You add them just at the very beginning, once you get out of your embeddings, but you don't add them again anywhere else. It's just after the embeddings. That information is persisted through the model at that point. Now, there are a lot of new versions of this, so it's worth kind of paying attention to the modern kind. They work slightly differently, so they don't have to be additive. They can be multiplicative instead. So rather than add something to my word embeddings, I can slightly shift multiplicative other vectors I have at different places in the model. So the most popular kind are called rope embeddings, so rotary positional encoding. We'll learn more about them later, but these take place somewhere else. And notice that we're really kind of modulating is shifting the direction of our vectors a little bit instead. So rather than saying add something in, we're saying take your vector and go ahead and rotate it a little bit. And that's what's going to carry this encoding information, this position stuff that we want to have in the model. OK, and these are slightly different. We're going to perform it in every attention layer instead. All right, let's pause there. We are going to run out of time, so let's take 1 minute to talk about these things. Anybody have questions? Yeah.
Why do we have I is a different value to x?
Sorry, wasn't able to hear quite that far.
So in the position embeddings, why do we add a different value to each index if we are just interested in this linear relationship?
We could. The problem is if we do that, it's actually going to like drown out a lot of our signal, right? And the second thing too is we're not going to be able, like think of the values that you'll have to use, right? If your sequences are up to 10,000 long, then what will have to happen? You're going to have to split everything up between 0 and 10,000. So you'll have these very, very tiny differences, right, that are consistent across everything. And that will make it very hard to optimize ultimately, right? So you're not going to have any differences between this position and the next position because they'll be so tiny. That's the intuition for it.
So I meant like within a vector
Yep.
to each index,
Yep.
we're adding a different value.
Yeah.
What's the intuition?
Yeah, if you avoided doing that, let's say you added exactly the same value each time, right? Then what would you do is you would say, OK, between the values of 0 and 1, I have to split up that range, right? You see what I mean? By the length of the sequence. So then the things I'm adding consistently would be very, very tiny differences between different positions. And that would be very difficult to work with. Great question. All right, let's go ahead and kind of proceed to the end, because we're getting pretty close to actually being able to design layers. And that means we'll be able to put it together into an actual transformer architecture. And what we'll see later on is that we can take this architecture and rip it apart a little bit and basically design all of the current language models that we're using, plus a bunch of other things. OK, so what's going to be our intuition? Again, we want to do this for translation. That was the original task that transformers were designed for. So what that really means here is we're going to take an input sentence in one language, and ultimately we want some output version of it in a different language. And the way we're going to do that is that we're going to design two kinds of layers, encoder layers and decoder layers. And how to think about this? Well, the intuition is something like this. My encoders are trying to get all of the relevant information out of the original sentence, while dropping the details of the original language itself. So I'm trying to go into some abstract, latent space that carries all the relevant information, but in a way that's independent of that language that it came in. And the decoders are, maybe not too surprisingly, doing the opposite. They're saying, let's start with this completely abstract language-free thing, and let's increasingly add language information in the language I'm translating into until it becomes some readable sentence. OK, everybody OK with this intuition? And this is a very standard intuition we'll use again and again. We'll often go from some raw data space into this abstract or latent space, and then from there, we'll decode back into something else that we care about. So this will show up all over the place. OK, now we said we're getting rid of recurrence. That was kind of our initial goal. We're going to replace this with self-attention. That's the operation that we've just defined. And now we can start talking about this architecture that we've seen a bunch of times. I promise that we'll go through this. You can kind of already start seeing elements in here that we've been talking about. So we had our inputs over here on the left, right? That was going to be our sentence. We said we're going to tokenize it. Then from the tokens, we're going to go ahead and get our input embeddings. Those were just the word vectors that we talked about, those X's that we had in green. Then we said, OK, let's add our positional encodings. Those were the sines and cosines that carried that information for each of our word embeddings. And then let's pass it in to multi-head attention. So we're seeing stuff that we've already talked about. In fact, the very beginning of what we're seeing here, we've covered. We know what's going on. Now, what are the differences? Even here on the left in this encoder stack, there are some things that we didn't talk about. We have this kind of add and norm. That's referring to a residual connection. We'll talk about that. There's also a normalization layer. We didn't talk about those things yet. And then finally, the part that's really new is the blue block that you're seeing above this. Those are going to be very standard feed-forward neural networks. And we'll talk about the intuition for that in just a second as well. But that's basically it for an encoder. Now, the other thing that you're seeing over there is there's this capital N times. We're going to repeat this encoder structure multiple times. Again, the intuition is just the same one from CNNs. We don't use one single convolutional layer. That doesn't take us to an abstract enough space right away. We have to do it repeatedly. And we just take the outputs from one layer as the inputs to the next. A standard deep learning kind of idea. OK, that's going to be enough for us to design an entire encoder layer, or an encoder stack. There are going to be some differences, but not too many for the decoder stack. That's going to do the opposite side and do the translation itself. Yeah?
Real quick, is the input to the left side layer that comes after this, so like the NX, is that going to be a self-attention head, or is that going to be a
That's the whole block.
Yeah, the block. The input's the block. Is it going to be a self-attention head, or is it going to be a cross-attention head with the original input embeddings?
Are you talking about the decoder side or the encoder side?
The encoder side.
The encoder side is going to have pure self-attention. There's no cross-attention anywhere. And the outputs are just what's coming out of the top of the previous encoder. You pass that as input to the current encoder. So it's just processed words until eventually we get finished with our entire stack of encoders. Can be. Sometimes it is. Depends. We'll talk more about that too. OK, let's start trying to figure out the encoder stuff. We'll talk more about the decoder in just a bit. OK, so let's go ahead and figure out what this architecture is going to look like. Again, to be completely formal, what we're doing here is a sequence-to-sequence model. The input is a sequence of words in one language. The output is another sequence of words in a different language. So again, sequence to sequence, if you think back to when we talked about these different models, multiple inputs, multiple outputs, in other words. We're going to have these stacked encoders and decoders. That is multiple versions of one kind of layer. Standard deep learning thing where we have many different layers. Here's what it's going to look like when we think about the overall architecture. Let's say that we're doing French to English translation. The input is going to be the French language version of the sentence. The output is the translation in English. Here's how the flow is going to go throughout these. First, I pass this input language sentence. Then I'm going to pass it into an encoder. The encoder is the thing that we talked about, but we'll zoom in just a second. The encoder is going to go ahead and process that sequence of vectors. It's going to produce another sequence of vectors. Now, this sequence doesn't pertain to language anymore exactly. It's just something more abstract. I'm going to pass that thing into another encoder. It's going to do the same kind of operation to it. Then I'm going to pass it into another encoder, and so forth. So I'm passing my sequence through this stack of encoders. I fix how many of these there are in advance. And then finally, at the end, I'm going to have just some bunch of words with vectors for them. OK, now these are going to be abstract. They don't pertain to any particular language. And now it'll be time for us to go ahead and do the actual translation. And this is where things will get slightly different than before. We are going to take all of these vectors that we get from the top encoder and pass them to the bottom decoder, let it do some operations, and then pass those up into the other decoders. But we're also going to persistently pass the output from the top encoder into each of these decoders. OK, now there's a reason for that. The way to think about that reason is something like, well, I don't want to forget all of this abstract information that I've developed with my encoder stack. So I'm consistently going to pass it in and do some work with it. However, this does complicate the picture a bit, right? Because if you look at these decoders, they don't have just one input from the previous decoder. They also always have two of these inputs, previous decoder plus what we get from the top encoder. So that's the one key difference that we're going to have to deal with when it comes to these decoders. They're going to work slightly differently, and they're actually going to have two notions of attention. Self-attention, the way we've defined it, and something else called cross-attention. And that's going to take us a little bit of time to build intuition for, but won't be too bad. OK, any questions about this high-level picture so far? Go for it.
Just to confirm, encoder block will only run once, and we will iteratively call the decoder step, right?
Well, the encoder has to happen for each of my input words, right? So you're also actually running that a bunch of times as well.
Yeah, but like for a sentence, after we have created a Z vector,
Yep.
and we have, that is the only, like it's kind of a pre-built step for that.
Yes. So each word I generate in my decoding has to get passed back in, and I'll reuse it. This is kind of getting ahead of ourselves a little bit, and you'll see what I mean. There is one annoying difference for the decoder. I cannot see feature words that I've translated, only the ones I've done so far. So I'll have to wait for each one to get generated, put it back into the input, and keep going from there. So that's one difference. That's what you're hinting at. You're going to see this in just a second. All right, so let's zoom in so it gets a little bit more clear. Let's start looking at the actual encoder bits. It's going to have two components. And in fact, it's almost exactly what we talked about. There's not too much going on here. I have my self-attention block that we just talked about. And then in addition to having the self-attention block, I'm going to add a neural network, like an MLP. OK, so why do I want to do these two things together? We have to go all the way back to our original sort of intuition, right? We said there's two things that we're doing here. One is that we're processing representations of words, right? We're saying for each word, I keep sending it up further and further through these layers, getting more information out of it. And we also said we want to permit interactions between words. Those were our two basic ideas that we wanted to take advantage of. Well, the self-attention block is the one that gives us these interactions. And then the fully connected layers, the MLP, that's what's going to give us these sort of processing for each word. And notice that we need both, right? Self-attention says, hey, give me information from related words. These MLPs say, hey, go ahead and create more abstract versions of the information that I care about. Everybody OK with that? So we're finally getting around to kind of the two things that we talked about earlier on. And the way we'll design the architecture is exactly just these two things. Run self-attention first to capture the interactions between words, and then go ahead and pass these into our feed-forward neural network. It's just going to produce other vectors, right? Nothing special going on. And then finally, we'll talk about the decoder part next time. The decoder is going to do one additional thing. So this is the part that's sort of different. It is going to do this encoder-decoder cross-attention. It's going to do something special, but this is really for the translation case. We'll see that we don't always actually need this. All right, so we have 3 minutes left. Let's go ahead and dig into the encoder a little bit more. This is the stuff that we talked about. We have self-attention. We know what's going on there. And then we have these feed-forward neural nets. They don't apply to combinations of words. They apply to the vectors that came out from self-attention for each word. So here's what it looks like. You can kind of see the difference between these two kinds of blocks. In self-attention, I need to do something with both of these guys, right? And in fact, I need to do things with all of these words because I am comparing their query and key vectors. However, afterwards, I don't have to do anything with interactions. I take these outputs, Z1, Z2. Each of them independently gets passed through a neural network. And that's what you're seeing in blue over there, this feed-forward neural network. And then I take those guys' outputs, and I'm basically done with this block. I can use them as inputs for the next block. All right, everyone comfortable with these two elements that we're going to use in our encoder layers? And again, your intuition should always be self-attention is about interactions, and then all of these MLPs are just going to be about processing the information in each separate word. Interactions are not considered at that port. OK, now there's going to be slightly more elements here. We're going to do a bunch of deep learning tricks in addition to this picture. We're going to add residual connections. These are going to make training a lot easier. We're going to add layer norms. That's going to give us a lot more stability. But these are not themselves the things that really matter about transformers. It's just this very basic picture where we're separating this idea of processing word information and handling the interactions. If we've got this down, we'll be comfortable with everything else too. All right, we have 1 minute left. Any questions about this so far? And we'll pick it back up next week. Go for it.
When we will have multi-threaded instance data, it will be a matrix.
Yes.
So are we applying CNN there, or we are just mating with the histories and then applying it?
So the multi-head attention itself, we're just going to concatenate. So we really just have vectors for each of our elements in the sequence as well. So nothing actually is going to happen special. If you're looking at that picture from before, I'm just stacking all of the words, right? But here, notice that I'm de-stacking them. Do you see what I mean?
Yeah,
Yep.
vertically stacking, right?
Yeah, but this is for every element in a sequence. But when I run the MLP, I'm taking these apart, right? So that's what you're seeing there. Yeah.
What is value of this? Can I get an intuition of it?
It's just something that is going to be used. It contains information about the word. And all I'm doing with it is saying, hey, I'm going to combine multiple values if they come from relevant words. Now, exactly what's in the value vector, I don't know, right? The network will decide that when it's trained, basically. Yep.
I'm just curious, like, how do I code this?
I need to give you. Perfect, yes. Yeah, I did. Yeah, we'll be good.
One token, and then we pass it into a network.
No interactions. Just there's one neural network, and I pump separately each of my outputs into it. Yeah. They're all the same. They're determined in advance in the model. Now, how do I pick those numbers? That's kind of this design of neural networks. I have to decide by experiments. There are a lot of known values for these. The way people do them is they say, okay, I'm going to experiment with 3 different. I'll pick the one that works better, right? And they do a lot of really small scale experiments where these models are not so big. They see how well it works and they pick out their. Yeah, we'll talk about this when we do scaling laws, which will come later. But there's no there's no good answer. It's not like, oh, I have a theoretical result that tells you exactly how to pick these values. You literally just empirically try different ones.
So another question is,
Yep, that's correct. So what I'm really saying for the softmax is I'm saying, hey, I have, for my current word that I'm working on, I have its value vector. But I want that value vector to get affected by other relevant value vectors of other species. Right, now the question is, well, how relevant should they be? Profile softmax tells you that information.
oh, that's why we the whole query and key is just to calculate.
Yes, that's all they use it for.
I have questions around cross-attention, but I will maybe
sure.
ask next.
Or feel free to come to office hours this afternoon. We can chat more.
Yeah, I have because there's something.
Okay. Sorry about that. Yeah, we'd find a different time or next time.
Yeah, okay.
Just for next week, have we ever cracked sublinear attention? Because I feel like most papers right now are getting it to linear.
Yes.
Like through low rank, or just like making it sparse, or just like a kernel trick where just like the operation
Correct.
is now just linear.
So the answer basically is you have to lose something to go sublinear.
Yeah.
Right? Because I mean, in the end, if you don't look at every word in a sentence, and to be sublinear, that's what it means, right? I have to skip some words or something like that.
Yeah.
So there's no way to do it while preserving all that information. All you can do is say, hey, I want to compress my original sentence in some very aggressive way, and then run on the compressed version with linear attention.
Yeah.
And then you get the sublinear overall. But this all depends on the compression, right? So that's the hard part.
I do not have.
But you see what I mean? Like it's not actually possible to really do something without giving something
So,
up.
But it all depends on like you have sequence and you have to find a way to remove redundancies.
Yeah, correct.
That would be just a way to keep.
Yes.
Otherwise, you
Yeah,
just
because there's always a possibility that somewhere in your sequence is the most important token, right? And that if you ignored it somehow, then you've done everything wrong, basically.
right.
So without more assumptions, you just can't.
So sparse solutions are just using findings from
Yeah.
attention layers, and you're just like, oh, this
But
is
even
where
even the
it's
sparse ones are not really sublinear, right?
Yeah.
At most they're linear, but yeah. We'll see that there's ways to do it that are log linear. So, right, n times log n, right, is what we'll try to go for without losing information. But that's actually going to turn out to be like the optimal limit. Anything below, we have to do approximations or compressions or things like that.
awesome. All right, thank you.
Yep.
Hello, IP Mark, and I have a question about this part. So,
Yes.
why do you say that the
Well, before we did this bit, right, notice that nothing here was about what index I'm at, right? Because that didn't play a role. Like the value I, or where I'm at, the position value, where never did anything, right? So I need to inject it somewhere.
well, won't the model actually learn
No, it doesn't know about that, right? Yeah. It just doesn't have any information about that. Mop those words, and it would still use them in self-attention. It would still compute them for computing the value vectors, right? Yep. They process each word, but they don't know anything about the position you're at either. Right? They just say, okay, well, send me my output from self-attention, but it doesn't know anything about the fact that this was the 14th word or the second word or anything like that.
I see. So, then about the context
I'm like,
thing.
I need to walk through.
So the major bottleneck for increasing the context length will be the position.
No, those are easy to compute, right? This is a formula. I literally plug in position in I, and I can compute all of these guys. So this is very easy to compute, and then it just produces vectors for each word, and I add them in. So this part's trivial, there's no big deal. The real problem with how long my sentence is when I'm doing my self-attention, right? Because what do I do there? I look at each word, and then for each word, I take its key, and I compare it, sorry, I take its query, and I compare it to keys for all the other words. So I'm doing this n times, one for each word, and each time I'm doing n comparisons with every other word.
Yeah.
So I'm doing n squared operations for each self-attention, right? But n squared here could be very big, right? Because my sentence could be length 10,000.
Okay.
That could be not a sentence, a document, right?
Yeah.
Okay, so that means I'm doing 10,000 squared every time. That's a very big value.
Okay, so the major limitation is the computation of.
Yes, exactly.
So doesn't so you're saying that the computation is during training or is it
Both
during-
training and inference, because I pay this penalty both times.
Okay, so
When I'm running inference, I'm still doing generation of these tokens, which means I still have to do self-attention, right? So I have to do this thing every single token I generate. And not just once, but for every self-attention block, for every layer.
I see.
So it'll be both.
So if the model is being the speed company is putting out like capable of context
Yes.
tokens, right? So that means that their models are trained with the context length of K tokens.
That's a second thing. There's two things going on here, right? One is if I train on sentences up to a certain context length, will I be able to do things that are longer at inference?
Yep,
So this is this generalization issue, right? So that's one thing. The second thing is, can I even pay the computational cost of a long enough context, right? Which is a separate question. So as long as I'm willing to pay the cost, I can do any length of sequence I possibly want, no big deal. But you're right, if I didn't train on those, then I can easily break down as well, because it might be hard to generalize as well. So yes, these companies care about both these things. They have tricks for both of them. They have these very fast approximate versions of attention, so that means that the n squared cost is smaller when you actually go run it. And the second thing is they have these like generalization tricks. These are tricks to say, even if I never saw an extremely long context window, I have ways of dealing with that basically. So they do both. Well, one problem is we don't really know because they don't tell us intuitively. So that's the other problem. But there's some papers that have tried like open source versions of this. We could talk more about that. Yeah, but I mean, so one way to basically do this is almost all my conventional training, I concluded, and then I do a post-training run where I take these sort of slightly longer than where I'm at versions, right? So I've trained on things that are up to length 8,000, right? And then I say, okay, now I'm gonna go ahead and create like a curriculum of slightly longer lengths.
Okay.
Go from 8,000 to 10,000, 10 to 12, 12 to 14, etc. And I don't do a ton of training like this. It's not in my big pre-training run. It's just a post-training adaptation.
I see.
There's a few other things that people do as well. Like one dumb trick that people do is they basically say, hey, I'm gonna do chunking. I'm
Okay.
essentially gonna say, instead of like working with a very long input context, I'm gonna split it up. And I'll find some way to glue together the pieces separately, even though they don't actually connect to each other inside the model itself.
I see.
So there's a bunch of tricks for it. None of them
Those
are right,
major,
but yeah.
mostly tricks, right?
Yeah, I mean, it's not an adaptation of the architecture.
Okay.
The actual change in the architecture to go subquadratic, we'll talk about that next time. That's a whole different model, though. That doesn't work like this anymore.
Okay, thank you.
Yeah. I think we'll be able to do it, yeah. Yeah, just wait for me. Yeah, go for it. Yeah, you're good.
Can I come to the office yesterday?
Yeah, of
I
course.
spoke to June yesterday, and like it's going in a different direction. So
It is
it's
going
kind
to
of
go in
my
a different
place
direction.
right now. So I
Oh,
just-
we can talk about that, yeah.
Yeah, you can come at 2:30.
Yeah, sure. Okay, I mean, it's a very bad analogy, so don't take it too seriously. So over there, the keys are going to be like the times that restaurants are open at, right? And my query is about like, restaurants near me or whatever. But I completely made this up, so don't take it too seriously. A real retrieval system will be very different from that. Now, okay, when actually we transform these things into vectors, we do not really manually encode information about what should be in a query and in a key. We let the model figure that out, right? And how does it figure it out? Well, it's adjusting the weight matrices for the queries and keys. So it'll say, hey, I've learned a good linear transformation that creates what is meaningful queries and keys, and that produces a good way of getting the interactions done. That's how it works.
So was there any previous work before this that included key query and key, or this was the first thing?
No, very similar older attention operations did very similar things. They also said things like, hey, I need to have, some comparisons between two of my words, and then I have, based on that, some other thing that I pick up on. So they don't have this terminology as far as I know, but like they do essentially the same thing.
Okay.
The only other differences are things like, I could have the same vector that I serves as both query and key. But this turns out not to do anything special, because different parts of that vector will be the part that matters as a query and the part that matters as a key. So separating them just kind of saves you a little bit on compute. Otherwise, nothing really changes. But yeah, older attention operations are extremely similar to this. There's nothing super different.
And also you mentioned that we are doing a dot product here, right? So you mentioned that there are other cases.
Yeah, of course. Yeah, so I mean, the generalization of the dot product are any of the other inner products that you'd have, right? So rather than saying, A transpose B, I can do A times a matrix M transpose B, right?
Okay.
So that's
Reducing matrix.
exactly it. In fact, any metric learning operation could be plugged into here. And I don't have to stop there. I could go to distances. I could go to an entire neural network that takes the two vectors and produces a similarity score. Any of those things will work.
Oh, okay.
But the problem is, I'm going to be doing this so many times, the cheapest, simplest thing is the easiest in the end. Yes?
So this is given to the for Q and K is given to like three or three matrices will have more performance.
Yep.
So if you multiply by 3 by 1, then like
Oh, so this guy over here is actually also going to be a matrix. I should translate that. So this V over here is a matrix itself, and this softmax output is another matrix, right?
okay.
So the elements of this softmax matrix, each one is going to tell you what those weights are, and those are going to get applied to adding the rows of this matrix to produce your final matrix of outputs.
Okay,
So every single operation here is between matrices.
this Q and K are 3 cross 1, right?
No, unfortunately no. So this guy is also going to be a matrix. So this X over here to begin with, this is like an N by D thing.
Okay.
So it's the number of words multiplied by the embedding dimension, because each of those words is getting one embedding, which is a D-dimensional vector.
Oh,
So you have a big matrix, and then WQ is another matrix, And it's really just saying, hey, I'm going to apply this entire linear transformation to every row of my X matrix, which is my word matrix. And this will produce another matrix, and this thing itself will be n by dq, right?
Okay.
Do you see what I mean?
Yeah.
And the same thing for all of these guys. Write down the like all of the dimensions and make sure it tracks.
Okay.
But yeah, it's just basically stacking all of the different elements into matrices and doing matrix multiplies instead.
Okay, I will try it once and for this.
Yeah, and tell me if I wrote it right, because it's good to verify as well.
Yeah, sure.
Hopefully I didn't write the wrong formula.
And in what data you're getting, right? You
Yep.
mentioned that, so like, can you explain this part, like what was
Yeah.
this image?
Okay, so over here, basically, one thing I could do, rather than adding the same integer that contains the position to every entry in my vector, I could just sort of take that position information, like a number, like here it's 37, and I could convert it to a binary encoding, right? And that's what you're seeing over here, 10100100, that's a binary, right, for 37, which is the position of my word.
Okay.
So one thing I could do is I could take this pattern and add this guy in, or maybe this pattern divided by some number, which is actually what that 10,000 looks like over there, but doesn't matter, right? So anyway, so this is what's going on here, right? I could do this, but here's one annoying thing. When I go from this position to my next position, all of these guys will go up or down, right? So I have these spikes, right? Just move sharply up or sharply down. Well, okay, that's not really great for my model. I like smooth changes because I have to do derivatives of all these things. Okay, so let's get a smooth version of this guy. That's really what you're seeing here, right? And these are exactly these sines and cosines that you're sampling from different places in the period of the sine and the cosine.
Okay, so this is the binary version of that 37.
Yep.
So we have to smooth things over there. That's
Yeah,
it.
exactly.
Okay.
Yeah.
And one more thing that you mentioned, position and location. So position is the, like, let's say for this one. This
Yeah,
is
it's
2.
2. Yeah, exactly.
And for location, like in this, like for this location, this is 3, right?
Yeah, exactly. Or, well, these are really all 0 indexed, but yes.
Okay, yeah.
Yeah, but other than that, yes.
Fine.
Yep. Hello.
What else do you want the second point is there?
Actually, yes, so there's like 5 open seats, so I'm going to try to get you guys in.
Okay.
So, yeah, if you could do that again, that'd be great. More, yeah, awesome. I think it should happen. I think we have enough space, but yeah. Yeah, absolutely.
Suppose we have a translation class.
Yep.
Okay, we have a statement here, a 4-word statement. Suppose we created the embedding, we did everything, we wanted to create an embedding. And now we are going to decode this here.
Yep.
Now we have done one, like we have got one out probability vector that will be basically the first word cut translation. And then that word is something, say, we are converting some other language to English and that word is I. Now that I word is fed right here, but it isn't fed, it's just like how the second word translation goes like.
Yep. I'm going to have over here one element in my sequence that came from the top.
Okay.
I have that literal, that's exactly what you're saying, it's the word. It's in the English language if I started with French. Now I have to do exactly the same thing as I did over here, right? Let's get that word's embedding, right? That's step 1. I have to add positional encodings again, because this is a new embedding that's separate from these guys at the input side. That's a different language. Okay, let's keep going, right? Then I plug it into here. Okay, the first thing I'm going to do is multi-head attention, just like here, with one single change. It's masked. And what does mask mean here? I don't yet have access to the features, so only mask it to see what I've done so far, which for us is exactly one word so far. Everything else stays the same. One more trick, I do cross attention instead. So now cross attention also brings in these guys in an attention layer. We'll talk about that next time, but that's one small change as well.
Just sorry.
Yep.
Say we have this I word in this, and we had some 4 words here.
Yep.
Now these 4 words as inputs won't go again to this.
No.
We will just use the
Yes.
like vector which we
Yes.
can say that have
Yes.
resembled
Yep.
the features of that input.
Yeah, we will never interact with these guys, the original raw words that we translated, except via the outputs from the Tom encoder. Beyond that, we've dropped them.
Thank you so much.
Yep.